Hello everyone. So today's session we are going to discuss about summing, scaling and averaging amplifier. So already we studied that op-amp is exist in three configurations: inverting, non-inverting and differential configuration. So let us first discuss about what is the value of summing, scaling and averaging amplifier in the inverting configurations. So the circuit drawn here shows the inverting configuration of an op-amp. So you can see there is 3 input is given to the inverting terminal of the op-amp. So we are going to find out what is the output in this session. Okay, so for that we will apply the Kirchhoff law to the circuit. So when we apply the Kirchhoff law, you can see that the current through the V2 node and V1 node will be equal to the output voltage. So for that we have to consider the 3 input, that is VA passing through the resistance RA will make the current IA, and VB through RB will make IB, and VC through RC will make the current IC. So these 3 currents will join into the node V2 and apply to the inverting terminal, and similarly there will be some current in the non-inverting terminal too, and we will get some output voltage at the terminal at the pin 6, and here the pin 7, and here the pin 4, and we have to after applying Kirchhoff law, we can say that IA plus IB plus IC will be equal to IB plus IF, where IB is the current through current that will be IB1, IB2 that to the inverting and non-inverting terminal, and IF is the current through the, that is the output voltage through the feedback resistance. And we can also say that since Ri, that is Ri, Rb, Rc and Rf, Rl, all these value, that we can generally say Ri, since Ri and A of the op-amp are ideally infinity, then we can say that IB equal to 0. IB equal to 0 ampere, and also we can say that V1 and V2, that the voltage at node V1 and V2 will be equal to approximately equal to 0 volt. Therefore the equation 1, that is here, the equation 1 will become IA plus IB plus IC equal to IF, and we can write the in terms of voltage and corresponding resistance. IA will be VA by RA plus VB by RC plus VC by RB and RC will be equal to V0 divided by RF, and here the V0 will be negative sign. So we can write in terms of V0, it will be minus RF by RA plus RF by RB, here VA also there, and VB plus RF by RC VC. This is the main equation for output voltage in the case of inverting configuration. Now we will discuss about what will happen in the case of summing amplifier. So in the case of summing amplifier, we can say the value of RA, RB, RC will be equal to R. Then the equation 2 becomes V0 equal to minus RF by R VA VB plus VC. This is equation number 3. If the value of RF is equal to the value of RA, RB, RC, then we can say that this value RF by R will be R by R and it will become 1. Then we can say RB equal to RC will be equal to RF will be equal to R. Then the equation 3 will be become V0 will be equal to minus VA VB VC. So in the case of summing amplifier, if it is an inverting configuration, we can say that the output voltage is equal to the negative sum of all input voltage. So output voltage is equal to the negative sum of all input voltages. All input voltages. Okay, this is equation number 4. And we can draw one. Okay. Next we will discuss what is happening in the case of scaling amplifier. So it will say scaling or weighted amplifier. Okay. So in this case we can say that each resistance RA, RB, RC each having specified value. So that is it each having weighted differently at the output. So we can say only that the output voltage will be equal to minus RF by RA VA, RF by RB VB, RF by RC VC. That is, each resistance have specified values, so different values. So the output of the voltage output voltage of the scaling or weighted amplifier will be V0 equal to minus RF by RA VA plus RF by RB VB plus RF by RC VC. That is, we can say that RF by RA not equal to RF by RB not equal to RF by RC, each having specified or different values. In the scale, now we will discuss the averaging circuit. What is the value of averaging circuit. So averaging amplifier, in the case of averaging amplifier, we can find out that here also the value of RA, RB, RC will be equal to R, and we can write the general equation as V0 equal to minus RF by R, VA plus VB plus VC. But here we can say that the value RF by R will be equal to RF by R will be equal to the 1 over the number of inputs. So that's how many inputs that we are giving. So the value of RF by R will be equal to 1 by that input. So we can say N is the number of input here, where N is the number of inputs given to the inverting terminals. So we can write the above equation will be like this: V0 equal to minus RF by R1, that we are having some value 1 by N. So I am writing here RF by R itself, VA, VB plus VC. This is the general equation. If in this example, in the circuit, we are giving 3 different inputs to the terminal, inverting terminal. So if this value will be N will be equal to 3, then RF, the gain of the circuit is 3 itself. Then we can write it as that is if there is 3 input, we can write if there is 3 inputs, we can write V0 equal to, that is 1 by N will be 1 by 3 VA VB plus VC minus 1 by 3 VA VB plus VC. This is the output voltage for a averaging circuit in the case of inverting configuration. So let's draw one red line here. So this equation is important. Okay. Now we will discuss about the non-inverting configuration. So in the case of non-inverting configuration, we are applying the 3 different inputs into the non-inverting terminal. Non-inverting configuration. So in the circuit, you can see that the input is given to the 3 different inputs are given to the non-inverting terminal. So here VA, VB, VC are given to the non-inverting terminal. Okay. Then similarly, here the node is V1. This node is V1, V2. Applying superposition theorem here, we can find out the voltage at 11 at the level V1, that will be R by 2. If in the case these all RA, RB, RC are R, then we can write V1 will be equal to R by 2 divided by R plus R by 2, VA plus R by 2 divided by R plus R by 2, VB plus R by 2 divided by R plus R by 2 VC. That is V1 equal to VA by 3 VP by 3 and VC by 3. That is VA plus VP plus VC divided by 3. It will be. Okay. So this is the equation for V1 here. That I will write the terms applying superposition theorem. With the resistance RA, RB, RC equal to R. These are the conditions that applied here, and we found out the value for V1. Now we can find out the value, the output voltage in the case of non-inverting configuration. For that, hence the output voltage that we get by V0 will be equal to 1 plus, that is the gain of the circuit, with the voltage at the node V1. So 1 plus Rf by R1, Rf by R1 into V1. That is V1 means V input. Okay, so V1. So here 1 plus Rf by R1. V1 will be VA, VB plus VC divided by 3. This is the equation for output voltage in the case of non-inverting configuration. Now we will find out the case of averaging amplifier. What is the averaging amplifier if it's in the non-inverting configuration? So averaging amplifier, so in the equation, I can write the equation as V0. This is the final equation. That will be equation 5. The equation 5 shows that the output voltage is equal to the average of all the input voltage times the gain of the circuit, 1 plus Rf by R1, hence the name averaging amplifier itself. So the equation 5 itself is given the equation for the averaging amplifier, that is the output voltage is equal to the average of all input voltages times the gain of the circuit, 1 plus Rf by R1, hence the name averaging amplifier. So depending on the application requirement, in the gain 1 plus Rf by R1 can be set to a specific value, and if the gain is 1, we can say that the output voltage will be the average of all the input voltages. Okay, so we can say that for a specified value of gain 1, if the gain is 1, V0 will be equal to VA plus VB plus VC divided by 3. That is, the output voltages will be equal to the average of all the input voltages. Okay, then next is the summing amplifier. So in the case of summing amplifier, we can say that the gain of the circuit, that will be 1 plus Rf by R1, is equal to the number of input. The output voltages becomes equal to the sum of all the input voltages. So we can select that the gain of the circuit is equal to the number of inputs. So in the above circuit, the number of input will be 3, so the gain must be 3. Then this is important, number of inputs. Okay, so here gain will be set as gain is equal to 3. Then the above equation will become equation 5 becomes V0 equal to 1 plus RF by R1 will be 3, and it will be equal to V0 equal to VA plus VB plus VC. So you can see the output voltage is, in the case of non-inverting amplifier, summing amplifier, the output voltage will be equal to the sum of all the input voltages. So here you can write output voltages is equal to sum of all the input voltages. Now we are going to discuss about the differential configuration. So for the basic differential op-amp configuration, a subtractor and a summing amplifier may be constructed for a differential case. In the figure, I drawn the basic differential amplifier used as a subtractor. Differential configuration is the third one. Okay, the circuit drawn here is a basic differential amplifier. Basic differential amplifier used as a subtractor. Okay, so in this figure you can see that we can give the input to the each terminals, that is inverting and the non-inverting terminal. So we can say the output of this circuit will be V0 will be equal to minus R by R VA minus VB. That is, if this resistance will be RF, we can write it as minus RF by R into VA minus VB. If we are giving the input signals can be scaled to a desired value by selecting appropriate values for the external resistors. So that when this will be done, we can say the circuit is referred as to the scaling amplifier, and we can write V0 will be equal to VB minus VA. This is equation number 6. And the output voltage V0 is equal to the voltage VB applied to the non-inverting terminal minus the voltage applied VA applied to the inverting terminal. Hence the circuit is called a subtractor. Okay, so this is the basic differential amplifier used as a subtractor, and we can also refer it to as a scaling amplifier because we are giving the input signal to the both the terminals, and the desired values can be selected by giving the appropriate values to the external resistors, and we can just refer to this as a scaling amplifier. So in this figure I just given that the gain of the amplifier is equal to 1, so that by giving all the resistance value will be equal to R. Okay, next we will discuss the summing amplifier in the case of differential equation. So the circuit is already drawn here. This is the summing amplifier of a differential, in the case of differential configuration. So you can see that we applied two inputs each into the inverting and the non-inverting terminal. That is total 4 inputs are given to the summing amplifier through the resistance R. All the resistance are given here as same, so that the gain of the circuit will become 1. So we can find out by giving that the output, that will be VA will be by applying superposition theorem, we can find out what is the output voltage in the of the circuit. For that we have to generalize that V output will be equal to V output at with the VA input is only the VA input is given to the terminal, and the other inputs VB, VC, VD will be 0. That's the output voltage of VOA, and another one is VOP. That is here the only the input voltage VP is given, and other output input voltages VA, VC, VD are make it as 0, and VOC similarly VC is given, other values are 0, plus VOD. VD is given and the other values will be kept it as 0. Okay, now we will just find out the output voltage. What is given will be the output voltage at VOA, where the other VB, VC, VD are given to 0. Other input voltages are given to 0. So the circuit for the particular is given into the minus R by R, and other output will be 0. So we can just count the value of input voltage VA only. So it will be equal to minus VA. And the particular circuit is given here. So you can see that only the VA input voltage is given to the inverting terminal, and other inputs are given here is grounded, so that there is no other input voltages. So the output of V0A output voltage will be only depends on the input VA only. So we can write it here, V0A will be equal to minus VA. That is derived here. Okay, similarly in the other case, if VB is given, all the other is grounded, and we can say VOB will be equal to minus VB, And now we will find out what will happen in the case of VC. That is, VC is given to the non-inverting terminal. So for that we have to first find out VA, VP and VD are set to 0, and we can say V1 equal to R by 2 R plus R by 2 into VC, and VC will be VC by 3, and we can find out the value of VOC, that will be equal to 1 plus R by 2, that is the gain of the circuit with respect to the input voltage V1 will be equal to, and this value will be 3, and V1 equal to VC by 3. We can say that VOC will be equal to VC itself. Similarly, we can say that if we are applying the voltage VD and the other voltage input voltages are grounded, we can say V0D will be equal to VD itself by deriving like this. So we got all the output voltages by giving only one input voltage at a time and grounded all other input voltages. Now we can find out the total output voltage V0, that will be V0 equal to that be written in the first expression, V0 equal to V0A plus V0B plus V0C V0D. Using superposition theorem, we can write V0A is V minus VA, V0B is minus VB, plus V0C will be plus VC, and plus V0D will be plus VD. So we can write VC plus VD minus VA plus VB. So in the case of differential configuration, summing amplifier, the output voltage of the summing amplifier is equal to the sum of the input into the non-inverting terminal minus sum of the input into the inverting terminal. That will be the equation 7, I think. Equation 7. Okay, so this is the value for differential configuration summing amplifier. So these are the two cases existed in the case of differential configuration: scaling amplifier and the summing amplifier. Thank you.